All right. So, wanted to make a video for you guys. My last class, unfortunately, getting some lag spikes here with the internet slowing down at like 3 p.m. So, my last class, I wasn't able to really lecture a whole lot. Today, we are introducing confidence intervals, and confidence intervals are a big, big concept. We are moving into inferential statistics now, which is huge. Now, we can actually use our statistical tools to make predictions on things we don't know. And unfortunately, with the lag spike, some of you guys I didn't give as good of an introduction as I wish I could have to some of this. So I wanted to make the video for you guys since you guys requested it in class and try to tie in some of the bigger concepts first that we were ending with in Module 4 to help motivate and introduce what we're starting with now, confidence intervals in Module 5. So if you want to follow along the lecture, I think I'm going to do most of this online. So I'll share my screen and just go through our digital interface of all the tools that we're going to be using. I might switch to a document camera and write some stuff out if I feel like it's necessary, but I'm not sure if it will be. So get open the Module 5 activity sheet, the Excel calculator, and actually, let me go ahead and share my screen. So I'll show you what I have open, let you guys get that open as well. This you guys don't need open. It's going to be a reference for us as to what's going on in the central limit theorem. So we'll have a little bit of module 4, just to touch base on kind of the end of the module 4 activities. And some of these things that we were getting into with the central limit theorem. This was our plumber problem that we had. Another good one to talk about, which will lead us into hypothesis testing, is this last problem here when where we were testing blood sugar. So I've got my module 4 activities. We'll talk briefly about that. Module 5 activities open. And then I've got Canvas open. And what do we want on Canvas? The other thing that might be good for you guys to get in the habit of just having open whenever you're doing activities, homework, anything like that, formula sheet. Going to come in handy for a lot of problems. So let's go ahead and click on that and get that open in a tab just for a quick reference. Because the other thing we want to talk about, I do want to introduce the calculator. Some of you guys, I wanted to introduce how to use it before getting started in class. Unfortunately, I think it was cutting out. And a lot of you guys might be a little rusty on all the little switches we've built in here and how to type things in. So I do want to go over that as well. So I've got the calculator. I've got formula sheet. We're going to be using these over here, starting in module 5. Some of the ones down here. Then I've got our activity sheets open. Module 4, module 5. Okay, so let's just refresh. Two big stats concepts. Actually, let me increase the font size so we can see all this. We'll just make everything big. Number 1. How do I, there we go. The bigger the sample size, the more representative. Let's say the more it represents. Let's say more accurately the population. This is just our English sentences. How do we interpret this in words in our own interpretation? Basic concept. It's kind of the DOI no-brainer. Bigger the sample size, it should more accurately represent the population. Sounds intuitive, right? And the second biggest stats concept is that small probabilities are significant. Just to say a few words on this one, since we're not going to quite get into it yet. We saw hints of this. This is going to be getting us into hypothesis testing. And this is really the crux of hypothesis testing, this concept right here. Why are small probabilities significant? It's almost counterintuitive to a lot of young stats students. And we saw a little bit of this at the end of module 4, and that's this blood sugar testing. This person may or may not have diabetes. We do one single test, and we calculate a probability that they get higher than 180. And we found, I think it was something like a 5% chance. Okay, so that could have happened. Then we do 2 tests, and now we're using our central limit theorem. What's the probability that the average of 2 tests is bigger than 180? I forget the numbers, but I think it was fairly small. I think it was like maybe 1% or even smaller than that. And then after 3 tests, it was like 0.002 or something like that, or like 0.2%, something really tiny. And in other words, we had a small probability. And that is significant. So small probability as being significant means that if we see an event that occurs that shouldn't have ever occurred, the probability of us seeing that should have been so low that it should have never even been witnessed, but yet we did witness it. It means that our assumptions are false, that our original assumptions, that the person's blood sugar had a mean of 120 and a standard deviation of 35, was wrong. Indicative that their blood sugar probably is actually higher on average. So that's just a little hint of that. We'll get into that. That's really the crux of hypothesis testing. And I want to talk about that again and repeat that concept again as it comes up, because it's very, very important for this class. But for now, we want to build on confidence intervals. And confidence intervals primarily deal with this first concept now. So we also saw this bigger sample size, the more accurately it represents the population. Well, this is a math class, so we want to turn this into, well, what does this even mean mathematically? This sentence is not a very mathy sentence. It's got some intuition to it. Bigger sample size accurately represents the population, but what does accuracy mean? What do we mean by more accurately? Can we measure the degree of accuracy? And what mathematical numbers do we use? What measurements do we use for that? And this is what we're doing with the central limit theorem and confidence intervals. So let's take a look. Let's go back to module 4 just real quick. Go back to this plumber problem we had. This was in part 2, central limit theorem number 1. And again, I don't have the numbers written out on my activity sheet. But what did we find when we compared these two answers from A and B? A sample of size 18 and a sample of size 32. And more importantly, that the interval straddles the mean. That the lower bound is less than the mean, is less than the upper bound. So last module, what we saw is that, well, the probabilities went up. And why should the probabilities go up with the sample size? Because the bigger the sample size, the more accurately it represents the population. In other words, if we are computing the means of our sample size, and we want to compare that, the mean of a sample with the mean of the population, then the bigger the sample we take, we should, on a higher probabilistic basis, with a higher probability, be closer to the population, right? The sample mean should be closer to the population mean with a higher probability of success if the population, or excuse me, if the sample size is bigger. And we see that with these distributions. So the picture of this, so to save myself some drawing time, is this diagram here. Within a fixed interval, what is happening as the sample size increases? So this was a question on the homework. Which of the following graphs represent sampling distributions with different sample sizes from the same normal population? If the sample sizes were 12, 14, 20, 27, which graph represents 27? So 27 is our highest sample size. So if we are taking a sample and measuring the mean of the sample, that mean should be much closer to the population mean. And so in the last problem with the plumbers, what do we mean by higher probability? Probabilities are measured as the area under the curves, under the distributions, with the total area under all of these curves is 1. So no matter which curve we choose, the total area underneath it is 1. And so if we fix an interval, something like here to here, and we look on different graphs at the same fixed interval, the same width, which one will contain the most area? Which one will have the highest probability of being within that range that we specify? That's going to be this one here, right? Most of the curve is between maybe this mark and this mark. So sorry, let me see. We can't annotate on Zoom here. So let me draw. Let me see if I can draw. Yeah, so let's say we pick fixed interval here. And it'd be best if we could line all of these up over top of each other, or vertically. You can kind of see that within a fixed interval, of course, the one with the most area is going to be here, whereas the one with the least amount of area is going to be here. There's a lot more left on the outside, a lot more in the tails, which means that the smallest sample size is going to be this guy, whereas the sample of size 27, the largest sample size, will be the one with the most area, because we expect the average of a sample of size 27 to have a higher probability of being at the population average, of being right within that window. Great. So that's what we learned last module. What are we getting into now with this module? And the problem with these types of setups is that we assume we know the population average, which is not necessarily true. So in confidence intervals, what we want to do, let's pull up an extra note sheet here to give us some space to write. Let's see, any notes we want to add. So can we measure the degree of accuracy? Let's maybe make a note on that, a mathematical note. So we looked at the pictures and we can describe it with areas. What else is happening with these shapes? How do we describe the width of the distribution, right? Some are wider, some are more narrow. In other words, we use the spread, the standard deviation, to measure how wide the distributions are. So in some sense, the standard deviation, and I'll say in particular of the sampling distribution, the standard deviation of the population is kind of just like the natural variation in the population. But as we take these bigger and bigger sample sizes, what happens to the standard deviation goes down. Again, on the activity sheet, we worked through some exercises with that. So in some sense, the standard deviation of the sampling distribution describes the accuracy of the sample. With smaller standard deviations being more accurate. Okay, so this brings us into confidence intervals. We don't know what the population mean is. So what is the best way to guess? Well, take a sample, right? And often we don't know what the population mean is because we cannot sample everyone. So what do we want to do? We want to take as big of a sample as we can. Sometimes we have to specify within a certain degree of error. Or sometimes we just take the samples that are available or samples we're capable of handling. And within that sample, well, now we want to be able to describe from our results, where should the population mean lie and how accurate? We'll write some of that out. So take a sample. And then given the constraints of the sample, namely our numbers, we can't sample everyone, the funding available for scientists and researchers. Of course, we learned at the very beginning, sometimes we have to rely on convenience sampling, which it may not be the best. Sometimes performing a simple random sample is hard. And of course, the bigger the sample size, the harder it gets to actually perform the sampling methods, more time, money, energy. So there's always a little bit of constraints. And given the results, what can we say about where the population mean should lie and how accurate are the results? So that's our goal with confidence intervals. So the best guess for the population mean would be the sample mean. If our sample is large enough, we should expect, whoops, sorry, I'm on annotate. Let me clear that, get back to my mouse. Right? If our sample is large enough, we should expect it to be very close to the population mean, but not exact, maybe. So maybe we want to build in a margin of error. So around the center of our sample mean, I want to go above a little bit and below a little bit. And so that is how we build our confidence interval. So how do we go above a little bit? How do we go below a little bit? That is with our formulas here. So let's go back. Let's take a look. Let's pull up our formula sheet. And it tells us how we build the confidence interval. And this is exactly what I just described. If we take our population or sample mean, I add a little bit of error, and then I take the sample mean and I subtract off a little bit of error, we expect this to be true. Now, this statement isn't always true. The population mean isn't necessarily in the middle, but we can say with a certain degree of accuracy that it is. And how do we want to build this margin of error? With this formula here. So what do we see about this margin of error? What is the sigma divided by square root of n? Let's see, is that on the formula sheet? Did we have it over here? Yes, we did. What happened to our sampling distribution standard deviation? As our sample size increase, the sampling standard deviation decreased. And moreover, it decreased by this dividing by a factor of square root of n. So really what we want to do is take the sample size and take the standard deviation of the sampling distribution. And now we're multiplying it by the ZC, which we call Z critical. Let's go over that real quick. Whoop, wrong sheet. What is ZC? Excuse me one second. Let me pause the video, take a quick break, and we'll jump in with that question. What is our critical Z value? And maybe I'll draw a picture. Might be the easiest way to answer that question. All right. Sorry about that. Of course, with the video pausing, it's not going to be too much of a blip or anything. So let's get back to what is ZC? What is our critical Z score? So we did this in the last section. This was a little tricky. These are our middle distributions. So this is one important fact about our confidence intervals. Confidence intervals are always a middle percent or always a middle distribution. So this 90% confident, we were working with these percentages in the last module on where does a percentage lie? Right tail, left tail, middle, two tails. Confidence intervals were always in the middle. Let's write that down. So confidence intervals are always a middle percent. I.e. the confidence level, which is given as a percent, 90% confident, 95% confident. Sometimes we'll see 98 or 99. Means that that percent is in the middle of the normal distribution. So let's just draw a basic picture real quick of that. What's the nice thing about z-scores? We know exactly all the information we need to. As soon as I give you a z variable, we know we're using z-scores. That's ubiquitous throughout stats, not like in calc or algebra where we can let z be anything. In this class, z will always be a z-score, and a z-score always deals with the standard normal distribution, where our mean is 0 and our standard deviation is 1. So what are we doing? Well, I want let's say we want a 90 or 99% confidence interval. We want a 90% confidence level. I'll use CL for confidence level, or 90% confidence interval for the full interval. Means that I want a z-score, and that's probably not big enough. Let's make it a little wider. So that's the middle percent between negative z and z, and let's call it zc, z critical, is 90%, the area within those. And then what are we doing? Why are we shifting everything? Well, so in a nutshell, we learned what's going to happen if we have a normal distribution and I add values, or if we multiply all the things by a specific value. We talked about what's going to happen with a distribution, whether it shifts up or down. So for example, if this is my standard normal distribution, but now I know my actual mean is 10, I want to take everything and add 10 and shift it. But I still want to keep that same interval in some sense. And well, how do I stretch everything? Well, I want to multiply all the values of the distribution by a certain value to stretch it out to match the standard deviation of our given distribution. This is, in a nutshell, what is going on with this confidence interval formula. So let's take a look. Let's go take a look at this sheet real quick. Let me switch to my share screen. So when we go back, the linear shift, I'm essentially taking the standard normal and we are shifting it over by x bar to match the mean. That's why we have x bar plus e and x bar minus the error. And then how was that error computed? Well, this error is the range, like the range we just had on our picture, except how do I shift that range? Well, we shift everything to be centered about X bar. And then I need to scale everything, stretch everything by the standard deviation. So I take the ZC, which is the critical Z value, right? The number of standard deviations we should expect to create this interval. And then scale it by the sampling mean, or the sampling distribution's standard deviation. So that's it in a nutshell. If we wanted to work out the math, I can show it to you privately, or we can talk about it in small groups or something. Usually, really what we're starting with is actually the population mean and building that same kind of interval about it, and then shifting it a little bit, doing a little bit of just kind of fancy math, fancy algebra with inequalities. It's not, I guess, not even too fancy to get this formula here for confidence intervals. Okay, so let's summarize that. ZC is the z-score. So that's the given confidence percent lies within minus z to z. And then I guess our last note, we then use ZC and scale the interval by the central limit theorem. Let's say the sampling distribution, standard deviation, and shift by the sample mean. So that ZC was critical. It told us where 90% of the data should lie, which tells us that 90% of the time, if we were to perform these sampling statistics, or if we were to perform this sampling method, let's say 100 times, then 90 out of those 100 times, this interval we create should contain the true population. Let's write that down too. Say our confidence level is 90%. Then this means that if we take 100 different samples with replacement, right? I take a sample, do a confidence interval, put those numbers back, do another sample, do a confidence interval. We take 100 different samples of the same size. Then 90 of them should contain the true population. And let's test that. So let's get into the calculations and how all the calculators work. I think most people were able to work this out in small groups, but the calculator is getting more fancier, I suppose. We've got more switches involved. So let's go over some of this. Open up the activity sheet from today. I think most people were able to get through this. Let's see. So this is module 4 activities. Need to save that. Let's pull up module 5 activities now and see how this plays out. And then let's take a look at the this confidence interval simulator, and we'll actually check it if the thing I just wrote has any validity. I think most of my other classes, you guys saw us do this, but it never hurts to go over it again. And my third class, unfortunately, we were lagging, so I didn't even want to attempt to throw this in there. And likewise, of course, the calculator was not going to work with a bunch of lag anyway. Okay, so let's take a look. Let's use our numbers that were given. We are taking a sample of officials that work in student services We take 55 people and we find their average salary, $73,490. So good things to do when you start your problems. List out all the basic information. We've got our sample mean, our sample size. We've got our standard deviation. And we've got now a confidence level. So I'll reread those. CL is 90%. So we write down all the basics. Of course, this is just good problem solving steps. If you end up solving the problem without using one of those key pieces of information, red flag should go off in your brain. I didn't use this, something's up. So if you've used all of it in your computations, chances are you're on the right track. And now let's take a look at the calculator. So confidence interval and hypothesis test. We are down here in the ints and tests tab. So just one more tab over from the normal distribution calculator. And of course, we've got some additional stuff that we can use for this module. So here we've got mod 5, confidence interval from point estimate and error, stuff you might want to try to program yourselves. Maybe I'll touch up on how to do the sample size. This was a tricky question, but I did want to, I think we might start class with that on Friday just to see how to work that out. I don't know if I want to put it in the video here yet. A lot of you guys were able to get that anyway. Okay, anyway, back to ints and tests. Right now we are just doing confidence intervals. So that's our first tab. What do we want to compute? A confidence interval, or are we computing a hypothesis test? Hypothesis tests come later, so let's keep it on confidence interval. What are we measuring? So far we've only dealt with sample means. What does our sample mean tell us, and how can I approximate the population mean? Later we'll talk about proportions, and that kind of relates a bit to the binomial distribution, where we might want to know what proportion of people have blue eyes. We can take a sample and we're going to get a proportion from the sample, and we want to approximate then proportions in the population. We'll get to that. So right now, let's keep it on means. And then I think the calculator may or may not have been updated. So I think the newer versions may not have this. This one was from earlier this semester, where our input is either statistics or data. I know some of the students today didn't have a data tab. So usually you can do this in a calculator, like a TI-84 or something, where you can do the confidence interval where you can simply just input the data set. You know, you can literally input the data you've gathered from your sample and then have it compute it for you. Or you can take the data you've gathered, compute the statistics on it. So we're going to be using the statistics, namely the mean, the sample size, the standard deviation from the sample, and then do your computations. So let's stick with stats. And I think most computers, or most of the calculators nowadays, they definitely have a stats. I think these disappear. So if they've disappeared on the new calculators and you're downloading it from Canvas, don't worry about it. If it's not there and it's in a new calculator, it shouldn't be needed. Populations, just the number of samples, the number of populations we're working with, just one at the moment. We'll do 2 sample stuff in the coming weeks. And then we want Z intervals. So a student asked today, what is the difference between Z and T? And Z is when we actually know the population standard deviation. And this might sound a little weird, right? What do we not know? The population mean. We have no clue what the population mean is. So we're trying to figure out how can we estimate the population mean? But somehow we know the standard deviation of the population. Doesn't occur a lot, and when it doesn't, when we don't know the population standard deviation, what do you think we do? We have to use the sample standard deviation. But that adds a little bit more error, right? Our standard deviation is sort of a measure of error. And if I don't know the population standard deviation and I have to use a standard deviation from a sample, well, now we're almost kind of like 2 steps away from information in the population. So we're introducing a little bit more error. And that's a different set of distributions, and that's what the t-scores are going to end up statistically being better for. But sometimes there are situations, right? If there's like a linear shift, let's say we knew data from the past. Let's say we're measuring salaries or something like that, and we know how far spread out the salaries are from the past, and maybe we can expect the spread should be about the same. So we can use the population standard deviation again, but as time has gone on, we know that salaries on average have increased. So we need to maybe do another sample. We need to test where is our new average salary, and we can expect that the population, the standard deviation, has stayed the same. So situations like that is essentially what we're working with now. So we want to do an interval. We're doing z-scores. Knowing the population standard deviation, again, removes a source of error. So it's a little bit more accurate, and that's what z-scores are going to be. They're going to be the most accurate when we're capable of using them. And we just go ahead and type in our stats. So what were our stats from the problem? Type in the mean, type in the population standard deviation, type in the sample size. Let's make sure our confidence interval is correct. We want a 90% confidence interval. And then computes everything for us. So one tip, this has been happening with a few people, it happened with me as well. You might be seeing, like, if you see hashtags on this, it just means that the number of digits here is just too much to display. See, if I shrink this cell I, you might be seeing that. Just go up here to cell I and make it wider, and then it'll display. It's just because we're using numbers. I think, right, most of the numbers we use are in the order of 0 to 100. Salaries, we're using numbers 0 to 10,000-ish, 100,000-ish. So a lot more digits, and it's just a matter of Excel not being able to display it. Okay, so we've got our confidence interval, our lower bound, is 69,189. Our upper bound is 77790. And that is our confidence interval. What is our error? So error, we can compute in two different ways. So in the first way, we can just use the formula, plug and chug, and go ahead and compute it. A little tricky, but if we also know that, notice that up here that the confidence interval, well, the x bar, the sample mean, is right in the middle. And what is the error? The error is the distance above and below our sample mean. So there's three different ways we can compute the error if we're given the confidence interval. We can either take the width of the confidence interval and divide it by 2, or we can take the middle value, which is our sample mean, and subtract off the low value. Or we can take the high value minus the middle value. And I think I missed a 7 back there. So all three of those calculations will give us the error in this. And of course, the activity was to see what happens to this error as the population standard deviation decreases. So again, population standard deviation you can think of as the variance in the population, and hopefully you can kind of guess that if the variance in the population gets smaller, then if I'm taking samples from that population, then the variation in the sampling distribution, the variation in the different samples we take, will also decrease. In other words, the error will decrease. Okay, so I think that's about it. Let's go ahead and check out this confidence interval summary and see how accurate we are with something like this. So let's click that link. Oops. No. I'm copying and pasting. If I click it, it won't open with my default or with Chrome. I want to open it with Chrome. Go there. Here we go. So let's use our information. So method, we want to go to means, right? We haven't gotten the proportions yet. Normal, Z with sigma. And let's go ahead and fill in our numbers here. So our sigma is 19,390. N was 55. And then we don't know the population mean. So just for illustrative purposes, let's go ahead and use that sample mean, 73,490 as our population mean. And let's now do this process of, if we know the population mean was this, 73,490, and we do this confidence interval process over and over again, and so we generate 100 different samples. So we're taking 100 different confidence intervals. What's going to happen? This one was actually pretty good. So each of these, we see the mean here, 73,490, and then each of these lines is the confidence interval. In that middle, those dots, that's the sample mean. So we took a sample of size 55, boom, right there, there's the sample mean, and then there's the confidence interval built out of it. And you can kind of see that most confidence intervals contain the true population mean, right? They overlap with this true population mean. And how many are bad? Looks like we're wrong 3 times. So you can build a confidence interval, and that confidence interval could be wrong. The true population mean might be somewhere else. But depending on the confidence level, so that was, that was a 95% confidence level. So with a 95% confidence level, we should expect only 5 to be wrong. We only had 3. So those results match what the confidence level we had was. Let's reset it. Let's change our confidence level back to our 90. Do it again. And now we see with a lower confidence level, we have more intervals that don't contain the population mean. So we were wrong 14 times, it looks like. It's like 86 of the 100 confidence levels that we made contained the true population. All right, so that was it. That was all the introduction for confidence levels. Hopefully that helps, and hopefully that'll get some good intuition for what's going on with here. Let me take a look. Anything else we want to add to these note sheets? I think that was pretty good. Hopefully you wrote some notes down, if it helps. And then hopefully you worked out all the calculator stuff as well. And we'll work on those, the additional tab in the coming days if you guys get to it. All right, I'll see you guys later.